Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right. If everybody will take your seats, we can get going again. So, just one announcement. The reception this evening, I have maps up here. It's very close to where we are now. It's literally, I'd say, a quarter of a mile from where we are. So it's easy to walk. It'll take 5 minutes to walk from here. There are maps up there. The basic trick is just walk up on one side of the parking garage or the other. The shorter way is to walk on that side of the parking garage, just to the next street, turn left, and walk up the street to the stoplight, cross the street, and you'll see it right in front of you. Microsoft has a big new complex of buildings. There's a soccer field there. There's a bunch of places that look like a store. The restaurant that's there is called Spitfire. That's where we'll be at 6 o'clock. So, everybody's obviously invited. If you need a map, they're up front. I have plenty of copies. So, all right. Back to the presentations. So there we go.
So my talk is going to be about work that's going on at Berkeley and at the UPCRC about applying image recognition techniques to image retrieval. And so we can start the talk while I guess while this is getting settled down. But I think fundamentally the problem that we're trying to solve is we're trying to make digital media actually worth something to people. And there's this needle in the haystack problem when you start getting a lot of digital media in your setup at home that you can't actually find it, and so you can't actually use it. And so I like to say that the incremental value of a new piece of data is sometimes negative, right? Because the more data you accumulate, the less you can actually use it. So that's a problem that we need to fix if we're going to keep moving forward. So the problem that we're looking at is trying to find images from consumer databases. So these are all pictures of my family, and I would like to find one that I'm interested in. How do I do that? So I'd like to talk a little bit about the spectrum that I see between image recognition techniques and retrieval. So there's already a lot of solutions out there for doing image search of various kinds. You know, at the one end where we're talking about things that have traditionally been called image retrieval, we have very lightweight search problems where we're looking at metadata search, where we have images that are tagged. And you know, if I'm looking for a picture of Jim in my database, well, it looks for all the pictures that have a tag of Jim and it pulls them up. There's a spectrum that goes all the way down to really deep image recognition techniques where we go from just looking at textual context and image tags to you know, looking at coarse features on images like give me the histogram of this image, and if I search for an image that looks like a mountain, well, you know, a lot of mountains have similar color profiles, so that might work. Of course, that doesn't work on a lot of problems, so we continually add more and more features, more finer features, until we get to the level of actually trying to understand the semantics of what's going on in the image. And as we do this, we are going from, you know, computations per image ranging from milliseconds all the way to several minutes. And so the goal here in this project is to show how parallelism can sort of shift the kinds of things that we do in image retrieval and bring things that traditionally have been far too expensive to apply to image search into the domain where we can actually think about that. So there's a lot of interesting computationally intensive algorithms that people use in computer vision, and we saw some great talks this morning that were going over some computer vision problems. The ones that I'm going to talk about today that we've been working on are really high quality image contour detection and some machine learning techniques for classifying images, namely support vector machines. And so we see things like, for example, the highest quality image contour detector that's known today takes minutes per image, And with parallelism and rethinking the algorithms behind these, we take it down to seconds. So we're trying to make it so that we can apply techniques which were far too expensive to even consider for search applications and bring them into search. And so this is kind of the outline of what a lot of retrieval applications look like. We start out with a set of images. If we have a database, presumably we're incrementally updating this database. But as we get new images, we perform feature extraction on them. Then the user is going to give us a query. They're going to ask a question to this database. And that is going to be used along with the features that we have to train a classifier that differentiates between images that are interesting or potentially interesting to the user and those which are not. And then that classifier is going to be applied to the database, and things are going to be returned to the user, and iterate from there. So first, I'm going to talk about this image contour detection problem we've been working on, which falls under feature extraction. So one of the fundamental steps that we have to do to understand objects in an image is actually figure out what they are. So image segmentation is a very fundamental problem in computer vision, and it's closely allied with image contour detection. So once you have a set of good contours from an image, it's fairly straightforward to go to a good segmentation of that image. And what I mean by that is the work to find good contours can be on the order of several minutes, and the work to actually go from contours to segments can be on the order of 1 second. So these are closely related problems. And the idea is once we have segments of an image, we can then extract features from each of the segments and classify the segments and expose them for searching. But the problem is that image segmentation is a hard problem, and high-quality segmentations can take minutes per image. So let's talk a little bit about the image contour detector that we're working with. So firstly, it's good to point out that like most computer vision problems, this is subjective. The actual contours in an image depend on your perspective and maybe even your mood. For example, if I showed you a picture of a koala and asked you to tell me what the boundaries of objects in the scene are, some people might say that the koala's arm is a separate object from the koala. And they would be right, depending on their perspective. Sometimes you want to differentiate between the arm of the koala, and other times you want to say, no, the koala is just one object. So it's actually a very subjective problem, and the surprising thing is that humans actually agree pretty well on this problem. And so Jitendra Malik, who's a computer vision professor we're collaborating with at Berkeley, got together a group of undergrads and had them label a set of several hundred images and find all the boundaries and do multiple labelings for each of the images. And then there's some sort of correspondence problem to figure out what images are actually what. And it turns out that people actually agree, sort of, on what the important contours of the image are. And as you can see in this middle image right here, we've got overlays of a lot of humans' interpretations of the koala. And you can see that there's only like one person that decided the arm was a separate object from the rest of the koala. But it's still an important piece of information. And on the right here are contours that are generated by the algorithm that we're talking about. And so when we talk about accuracy of image contour detection, we're going to be basing it off of ground truth on this test set of images that people actually hand labeled, because our goal is to find objects that people find interesting. And so speaking to that, here's a precision recall curve. So that's related to this false positive curve that ROC curve that people were showing earlier. So for any of these kinds of detectors, there's a very straightforward thing to do, right? So I could say, if I was really concerned with never labeling a pixel as an edge, I could say this image has no edges in it. And I would be right, in the sense that I would never label a pixel as an edge that's not a pixel. However, I wouldn't find any of the pixels which are edge pixels. And so that would be over in this regime, where we're high precision. We're never claiming that a pixel is an edge when it's not, but very low recall in the sense that we didn't actually find any edges. Conversely, we can label every single pixel in the image as an edge, and we will for sure not miss any edge pixels, but it won't be very useful. So there's always a trade-off in these kinds of algorithms between precision and recall. And so the goal is to be as far up close to the top and to the right as possible. Sorry. So this algorithm that we're working with, called the Global Probability of Boundary algorithm, published last summer. It's currently the most accurate image contour detection known. This graph is showing, like the past decade of computer vision research. They went through and found the papers and applied the techniques from these papers to their database and showed that, yes, actually they are improving the quality of contours. And we've gotten it to this point, this red point. If you boil down the curve into a single number that kind of maximizes both precision and recall, it's called the F metric, then humans are at 0.79, and this algorithm gets 0.70. Something like the Sobel edge detector, or the Canny edge detector would be somewhere around 0.5, 0.5. The problem with this algorithm, even though it's getting pretty good and it's finding really useful boundaries, is that it's very computationally intensive. It runs about 3.7 minutes per small image. And that's a 0.15 megapixel image, so it really limits its applicability. If you tried to index all the images on the web, by the time you actually went through, even applying a big, huge data center to the problem, there would be so many more images you wouldn't be able to keep up. So this is a really computationally intensive problem. And so we've been looking at parallel algorithms and implementations for this algorithm, and we have brought down the time for image contour detection from about 4 minutes to 2 seconds using very parallel algorithms on NVIDIA graphics processors. So I'll talk a little bit about that. So this computation, what I want you to get from this slide is that there's a lot of pieces to it. There are things like machine learning algorithms like k-means, where we're doing clustering on the image, traditional image processing things like convolving by filter banks, some other computer vision things that are used in other approaches, such as non-max suppression and intervening contour codes. We have a big generalized eigensolver, which was actually the most dominant part of the problem computationally. I'll talk about that in a second. And other image processing things like skeletonization. So there's a lot of things going on in here, and we worked on all of them. So just to sort of give you a flavor of what kind of computations we're looking at, k-means is a clustering problem where you start out with unlabeled data, and you need to cluster that data into k clusters, and the way that's done is basically by the guess and check method. So you start out and you assign random labels to all of your points, and then you figure out where the centroid of all of the clusters implied by those labels are, and then you relabel the points based on which centroid is closest to each point, and then you iterate and hope that you converge somewhere. And this is done on the image to find important textures. So the image is convolved with a set of universal textures, and these correspond to feature vectors for every pixel, about 30 elements long, and then we cluster those into, say, 32 or 64 different clusters. And that gives us sort of a way of ignoring some of the noise in the image while still finding similarity between pixels. So another thing that's going on here is gradient computation. We're looking for edges, so this is kind of a way of suppressing noise when we're looking at edges. If you imagine 2 half disks centered at every pixel, each of them are oriented at some orientation and have some radius. If we sum up all of the responses in each half of the disk and compare how different those are, then we get a metric of how strong of an edge we have at that orientation, at that radius, at that pixel. So we looked at this. The original implementation actually went through all of the work of summing up pixels over each of these half disks, and we decided there was a better way. So we changed the algorithm to use integral images. Integral images are basically a way of using parallel prefix sums, which have been around for a long time, to do these sorts of computations where we're doing sums of overlapping windows on images. And the way it works is you basically take a window of, you basically do a computation where the value at each point is equal to the sum of all of the elements to its top left. So for example, this box, if I do the integral image, then it's going to turn into a single pixel right corresponding, let's see, where is it? Corresponding about here in the image, and that's going to be the sum of all of these things in here. And this allows us to avoid repeated overlapping summations. So that brings down the computational complexity and really helps out. It's also good for parallelism because we've replaced a lot of histogram problem with scans, which have a lot better data dependencies. So the next thing that was really important computationally was this eigensolver, and this is a spectral graph partitioning approach. So we had some talks this morning about graph partitioning, and it's a very useful problem. The thing is, there's a lot of different metrics that you can apply to graph partitioning, and the min-cut method, which is the common one used in a lot of graph partitioning approaches, is bad for image segmentation and image contour detection because it tends to cut off lots of tiny little pieces everywhere. So min-cut is saying, I want you to break the graph that will disturb the fewest number of edges in the graph. But actually what that does is it tends to isolate things that don't have a lot of edges connecting them to the rest of the graph. And so if you change the metric from a min-cut metric to a normalized cut metric, where we're looking to minimize the number of edges that we cut that are normalized to the sum of all of the edges that are leaving the subgraph that we're cutting, that problem actually is much better for image segmentation. However, it's NP hard. And so instead of solving it directly, we approximate it with an eigensolver. So it's kind of interesting to show that these problems are related, and we can apply an eigensolver to this problem. So the other way to think about this is that this allows us to use global information about the things in the image to find boundaries. Instead of, the gradients that I was just talking about is a very local operation where for every pixel we're looking at a radius, trying to see if things are different enough to say there's an edge at that pixel. Instead of doing that, this is a more, it's a way of globally understanding the image. So every pixel is related only to a few pixels in the surrounding neighborhood. And we turn those relations into a sparse matrix that talks about how each pixel is related to some of its neighbors. And then when we find the eigenvectors of this matrix, it turns out to correspond to regions that should be grouped together. And here's an example of what it looks like. So here's a picture of a guy in a hula skirt and the eigenvector, one of the eigenvectors that comes out of this. So the thing to notice is that the eigenvector does a really good job of finding important boundaries in the image. So there's a lot of texture in here. There's a lot of confusion in the foliage back here of things that might be edges, but it's hard to say. And the eigenvector that comes out of this formulation is actually really nice. So the eigensolver problem itself is actually very interesting computationally. So in the Parlab, we happen to have a number of experts on sparse eigensystems, Jim Demmel being one of them. And so we went to him and said, Jim, we've got this eigenproblem. How do we solve it? And he helped us out doing some algorithmic exploration. And we found that using the Lanchas algorithm with this kind of not very commonly used technique called the Coulomb-Willoughby test ended up being the best choice for this algorithm. So these are the kind of results that we're seeing. So like I said earlier, the original code was running at about 3.7 minutes. We took it and parallelized it over a dual socket quad core system using p-threads and got it down to about 30 seconds. And our GPU implementation takes 2 seconds. So we can say that there's a lot of good parallelism there. And it's interesting to see how Amdahl's law bites us in one form or another for these different platforms. Of course, a lot of the reduction from the eigensolver is because we've changed the algorithm and gone to a more efficient algorithm for this problem. But these kind of results are exciting because this particular image contour detector is very powerful, but it's not very widely used because it's so computationally intensive. And we believe that with these kind of results, people can start applying this in a lot of situations where they couldn't before. Just some other data points about our GPU implementation. We actually ran it on a number of different GPUs. This is the same binary, just running it on a different number of cores, all the way from 2 cores in the integrated graphics that are now in Apple's laptops, all the way up to the GTX 280, which is the biggest GPU NVIDIA sells right now. And things scale pretty well. You'll notice that at 30 cores, we have 2 data points, and I somehow dropped a label, but the lower one is actually the Tesla board that has more memory but lower memory bandwidth. So we can see that this algorithm, that kind of measures the memory bandwidth dependence here. And also we can check scaling behavior in terms of image size to see what kinds of images we can handle. It turns out that we're limited on the Tesla board, because it has only 4 gigabytes of memory, we're limited to about 1.8 megapixel images, just because there's a lot of data that's generated in this process. But we can see that the runtime scales fairly well in the number of pixels. And most importantly is accuracy. If you're speeding something up but you've thrown accuracy out the window, then it's not that much of a help. So on this benchmark comparing against ground truth for all of these hand-contoured images, we achieved the exact same accuracy as the serial version. So kind of summarizing for this segment of my talk, I think that parallelism really is we really can use parallelism to practically take things that were much too computationally intensive to be widely applied and bring them into domains that they wouldn't have been able to address previously. And so I'm pretty excited about that. So the next thing I want to talk about is classification. So this is the process of analyzing images and classifying them as interesting or not. Or it can be used for other recognition purposes as well. So we have spent some time looking at support vector machines, which are a pretty widely used technique for classification. And in the content-based image retrieval context, using a support vector machine means finding a decision surface which separates image classes. And these classes are going to be defined by the search query itself. So the goal of the classifier is to maximize the margin between the classes, which gives us a pretty general classifier that hopefully is resistant to noise. So training an SVM is the process of you have a set of test images that you know the truth, and you want to learn from them the correct classifier. And it's a quadratic programming optimization process where we have the number of variables in this optimization process is equal to the number of test images that we have labeled truth for. We go through, and the goal is to find a weight for each of those images. And the great thing about support vector machines is that they can be nonlinear. So you can find a linear classification surface, which is basically just a hyperplane in some feature space separating positive examples from negative examples. Or you can use a kernel, which allows you to get rather nonlinear classifiers. But because of the formulation of the SVM, you avoid overfitting to your data, which is the common problem with a lot of nonlinear classification approaches. So to do this, we are actually using the sequential minimal optimization algorithm, which was invented at Microsoft Research by John Platt. I guess he's probably not here today. I was kind of hoping to say hi, but it's a great algorithm, and it's widely used in support vector machine training. What it does is, you may have several thousand, up to hundreds of thousands of test points where you know the truth, and the question is, well, how do I find a set of weights for all of these? And the hardest possible thing would be to update. You have some guess about the weights, and you update that entire vector of weights every time you make a step. And that's a full traditional quadratic programming method. Sequential minimal optimization goes to the extreme of only updating 2 of the weights at a time. So out of your 10,000 weights, you're only going to look at 2 of them. And in that case, the quadratic programming problem turns into a trivial one-dimensional problem that we could have solved back in high school. basically we have some constraints and they describe a box in 2 dimensions, and then we have another constraint that describes a line in 2 dimensions, so we're going to be maximizing over a line some quadratic function, and that's pretty easy. So what this means is that the actual optimization steps of updating the vector are trivial. The hard part is figuring out what those mean. So the actual work in the algorithm is computing some Karush-Kuhn-Tucker optimality conditions, which are basically done for every training point, and then you reduce over all of those to figure out which points you're going to be updating for your next step of your algorithm, and you just keep iterating. So we implemented this also on NVIDIA graphics processors, and we saw, using the Gaussian kernel, which is fairly widely used, we saw about 9 to 35x speed up over libsvm, which is the standard package for doing support vector machine training on CPUs. And so we were pretty excited about that, and we published a paper on it and put our software out on the internet, and I think we have around 250 downloads of it as of today, which makes me pretty happy. So people are actually using it, and the bad thing about that is that I get bug requests. But yeah, yeah, I guess that's right. I don't actually have to fix them. They just need to tell me about them. Right. So, and then the other side of using a classifier, I just talked about training it, where you're trying to find a decision surface. The other side is actually applying that decision surface to a database. And for support vector machines, that involves evaluating an equation, and it ends up looking like a big matrix multiply plus other stuff. And so we also implemented that and got fairly good results. We had both a p-thread version on the CPU as well as a two-way Core 2 Duo, as well as a GPU version using NVIDIA's graphics processor from 2006. So these results are kind of dated. But overall, our classification results were identical to the serial version when you took the classifier that we trained with our own training method and then applied it using our own classification method. They provided the same results. And I also want to talk briefly about another project that we've got going on in kernel dimensionality reduction, which is another technique for performing classification. In this technique, what we're trying to do is take a high-dimensional data set, like, for example, images with features on them, and we want to take it from something with really high dimension down to something with much lower dimension, like going from 600 dimensions to 20 dimensions. And in so doing, the classification problem becomes a lot easier. So in this, I think this picture sums it up really well. We've got this is from a 13-dimensional real-world data set describing wine, and it measured wine in 13 different ways, and then the classifier is it any good or something like that. And if you take that real-world data set and use kernel dimensionality reduction, the 3 different classes that we're trying to distinguish boil down into 3 nearly disjoint regions in the 2-dimensional space. Whereas other techniques for doing dimensionality reduction, they kind of tend to leave the data all on top of each other, which kind of makes it a lot harder to classify, right? So Mark Murphy in my group at Berkeley is working on this, and it's a non-convex optimization problem in order to train this thing with simulated annealing, gradient descent, and let's just cut to the chase. He's implemented a portion of it, and it's working pretty well. He's seeing fairly good speed up. So again, parallelism will work here. So I think that the challenge of all of this work is putting it together into a functional CBIR system that lets people search a database and actually returns what they want to see, and we're working on that. We haven't actually done all of that yet. We've been working on these components instead. But we believe that using more sophisticated feature extraction techniques like the contour detection I showed you, as well as more sophisticated classification techniques, will lead to improved performance. And that will let people do things they couldn't do before. And that's what we're trying to demonstrate in our work. So that's it.
So question here, so when the user provides the query into the system, do you solve the problem of open set? Maybe some of the query isn't labeled in the set. What do you do?
Right. So the way that we are looking at that is, so the user is going to provide some images that they're interested in seeing.
The sample.
A couple of them,
just
yeah.
Down what they want, like koala, for instance.
Right. This is content based. So the user says, I want an image that looks like this one.
So rather than using recognition to label whatever,
right.
object.
Right. No, this confusion is natural because they're related problems. You know, if I was able to go through my database and find all of the things that had a koala in them, and then I gave it an image that had a koala in it, if I could, figure that out, it would make searching it a lot better. I mean, it is performing this problem. So they are related problems, and we're coming up with a sort of hybrid solution that takes advantage of previous queries, things that it has learned about the database during previous queries, to augment queries and make them stronger that are coming from the user to try to find things.
It's not very convenient, right? Because you have to find some similar kind of image.
Well, so that's why we're working on exactly how to do that. But yes, there are CBIR systems that do things both ways, and we're trying to come up with something that makes sense. Yeah.
This is a question for anybody. How fast does it have to be for it to be a product? I mean, in the sense that somebody would take it and market it. I mean, how do you know when it's fast?
Right. So I think that there's two major components of these systems. One is the feature extraction stuff, which is kind of done offline. It's done when the images enter the database. And hopefully, that needs to be fast enough to keep up with the stream of images that are entering the database. Then the second part is the actual online part when the user is entering a query, and that needs to be, user tolerable. So what does the user tolerate for search? I think a couple seconds. So that needs to be fairly quick.
300 milliseconds for search.
There we go, 300 milliseconds from Jim Laris. So, yeah.
Great. Let's thank our speaker.
Hello. Am I on? Yeah. Thanks for fitting me in. Rick talked this morning about stuff we can do with large collections of images. We all know that one very easy way to get a large collection of images is to record some video. So I'll just talk about a bunch of work we've done in the area of video. And my goal with all of these explorations or my dream is to take the sort of effects that Hollywood people make today and ensure that my number one customer, the only person I know who actually does anything with video, which is my mother, can play around with them. One of the things, so this is my mum's laptop. She likes it very much. And I guess one of the funny things is why we've spent all this time saying that parallel programming is just around the corner. Does anyone know how many cores are in this thing?
4.
Is it only 4? That's
2 or 4.
Okay, in the GPU.
So you have to be careful, right? I'm using Intel definitions for core because we have Intel people in the audience. NVIDIA definitions for cores are slightly different. They would say there's 16 or 32 cores.
I see. The main thing is
using that to improve the core efficiency.
There you go.
the main thing is that the programming model is parallel. So we've been saying it's in the future. Well, it's already in the past in some sense because people who are coding for this thing are coding for a machine with, in their minds, in the programmer's minds, many more cores than are in it. I know you didn't like that picture, so I gave you a picture that's much more likely to be the kind of thing you like the look of. Okay, so what are we going to do? Well, here's a classic, here's a piece of video of my office, and I've performed a traditional video edit on it, which is I've overlaid a logo. And I've used some extra special graphics to make it nicely 3D, but it's not really 3D, it's just a 2D overlay on a 2D video. What we might want is something a bit more like this video here. So that the 3D object that I've embedded is living more in the world of the video rather than superimposed on it. So I can do this computation, but it's effectively the key to doing this, and now we can see the logo is beginning to appear again. The key to doing this is to run photosynth on the several hundred frames of video to generate 3D cameras. So the same 3D camera positions you saw before are now a smooth trajectory, and you render the 3D object with that. We've worked on ways to make it very easy to make animations like this one. So you thought the blink tag was bad when it came out in '92. You thought word art was bad. Well, this is the future. So again, these sort of edits, we know how to make the user interface very simple, but it actually requires a massive amount of compute to process the video in order that these edits are easy to render. There are still some problems with that. So, for example, this video is, I'm very proud to say, made Bill Gates laugh at that point. At that point, there was a sound from the man opposite me. So a great thing is happening here. One part of your brain, which does geometry and stuff, is really happy that this is probably on the whiteboard. That's where you think it might be. Another part of your object recognition system, which is looking at the relative depth ordering of objects, suddenly gets nastily broken when the TechFest goes on the background. And that's because despite all my protestations about 2D overlay on another 2D thing, you know, turning it into 3D, this rendering has absolutely no knowledge of the dense structure of the scene. So having spent lots of time computing the camera positions, we're now in a position to spend lots more time computing a representation of the scene which looks a bit like this. Now this is a pretty rubbish, this is a fast rubbish depth data where bright points are far away and dark points are near to the camera, so it's encoding distance. We obtain this representation by looking at the images themselves without using a depth camera. Because the scene is rigid, I can treat the frame-to-frame transformations. I can pretend that a pair of successive frames is a stereo view and recover a rubbish depth map like this. But this depth map is nevertheless enough to correctly occlude, to generate the clean occlusions that I get in this sequence. So we have the same thing again. But now it's less disturbing when the video passes through the audio. You'll notice it's still not perfect. There's a bit of boiling around here and so on. But certainly for home video use, or at least in the near term, you'd expect that this is not as disturbing an output as we had the first time. By the way, the reason I can use the rubbish depth samples is because I have access to an algorithm by Antonio Cremonesi and Tony Sharp at Cambridge, which they call geodesic image segmentation. But this algorithm is probably not interesting for this workshop because it's extremely fast. So you can process a large CT volume and generate these segmentations completely interactively. So we'll just skate over that. OK, so I said that one of the reasons I could recover depth from that sequence was because it was a rigid scene. You'll notice that there weren't any researchers running backwards and forwards in front of the whiteboard. If we'd been studying tracking, there would have been lots of researchers, but no moving camera. I've always wanted to be able to process scenes a bit more like this one. So you have an object like this giraffe, which is sort of undulating and articulating as it moves through the scene. We have a pair of giraffes, one occluding the other, and the camera's panning. So I want to know how to deal with non-rigid motion and what the representations are for doing that. So one of the things, a very simple thing that you might want to do if you've got a video, is attach an overlay, but have the overlay look like it's following an object in the scene. So, clearly the only application any of us can ever think of for anything is advertising. So let's assume that that's what we want to do here. So, OK, now that's got to be simple, right? What am I going to do? I'm going to click on some point on the giraffe, and we're going to follow it through time, moving the object. That's got to be easy. And indeed, it's not bad, right? So here's the interface written in MATLAB, for anyone who knows. This is extremely slow. The user has clicked on the giraffe's eye, and the cyan trajectory represents a search throughout the whole video. So there's 200 frames of video. So it's searched for points matching the giraffe's eye at about 200 frames a second, 400 frames a second. And what the user is doing is scrubbing backwards and forwards through the video and checking that the trajectory is correct, even though the back giraffe's eye was occluded during the transformation. So we're kind of looking at the position of that point throughout the video, overlaid on one frame. And you can see that basically at this stage, so he's having a good check there because the other giraffe's nose came in front. OK, so the user is happy that he's correctly tracked the video. In this case, it was 2 clicks. We have other examples where a 20-minute video that we managed to process in 3 minutes, including the user interaction. So this 8 times real time means including the user starting from the point before the user touches the mouse. The key is that you need to store 24 bytes per pixel to store a KD tree for every frame. So in order to do this, there's a massive amount of backing store. So we pre-compute on the video, and then we can get it fast. So that's something we want to deal with. OK, back to this guy. Well, can you see what I've changed? Oh, look, a new house has appeared. That's an easy edit. We could do that in the 90s. What is the representation that allows us to do that edit? This is a tricky edit, so I'm going to put something on the giraffe's neck, and it should follow the undulations correctly. We couldn't do this in the 90s. We can do this now. We're happy with that. What's the representation that allows me to do that? Well, again, I load up the video. I crunch on it for several days. And after several days crunching, I end up with a representation of the video that looks a bit like this. I split it into two static photos, a foreground layer and a background layer. This giraffe, the one in the background, didn't move enough, so he just got locked into the background. So his neck lifted, but that didn't get noticed. So I crunch on the video, I split it into these layers, and then I can do something like attach houses in normal photo editing to this layer and generate the image we just saw. Okay, so there's the background layer. I just use whatever photo editing technique I like to put in the houses, and then when we re-render, we get the image the sequence we just saw. And then finally, this allows us to deal with more complicated structures. So this guy's face, if you watch his mustache, you will see that it appears slowly and flashes on and off. The same sort of technique. Again, this is a 3D object. It's a non-rigid 3D object. And what photosynth would do, the photosynth philosophy, which I adhere to, is you would take this object and reconstruct a three-dimensional interpretation of what's happening. Well, what we decided was we'd reconstruct a two-dimensional interpretation of what was happening. So instead of reconstructing into 3D, we reconstruct into 2D, pasting all the new information from every frame of video into this representation, which is called a mosaic. And now you can draw on the representation itself. So we're drawing sort of on this one picture, the eyebrows et al. And then we can re-render those, mix them in with the original video, and generate this effect, which is reasonably convincing. And the mustache disappears correctly as it's occluded by the subject's face. Okay, so that's some stuff you can do with video. As we know, it's a splendid source of embarrassing parallelism. If you can get the video to the cores, so we want to do lots of computation on a big chunk of video. For many of these computations, each core would like to see all the video at once. Sometimes you can splice it up by frames, but sometimes you'd like to see all the video at once. And so given that you've got the video down at the cores, we can do lots of stuff. Most of the stuff I want to do turns a 20 meg video into half a terabyte of data. So actually, a lot of it is disk bound rather than RAM bound or CPU bound. But things are getting close. So that thing happens, and then, as in photosynth, you get some sort of order n squared or n cubed gather. So we do something on every frame. Then we want to haul all that information back. Not normally a load of data coming back. Let's say 20K of data per frame. But then you do some horrible gather of size n cubed. And that's because the non-embarrassingly parallel sequential algorithms that we love in video, you might think, video, you just do stuff on every frame and throw away the old answers. Always a bad idea. If you've got 99% reliability frame to frame, and your video is 1,000 frames long, 99.9 to the power of 1,000, or 0.99 to the power of 1,000, is a small number. And then, of course, we've just got the standard stuff. If I want to render this video with 100 different image processing operations per frame, I need to decide how to split that over whatever cores I have, but that's a standard problem. Right, thank you.
If there are any questions? Thank you.
Oh, there's one over there, sorry.
So some of this is going to be done very slowly offline, and then beyond the user's patience, and then something fast happens for the user using all that stuff that's sitting on disk. And so what would be done, for example, is drawing the mustache, but the face had been processed offline. Is that right?
That's the idea, yeah. But sometimes something we would love to do is half the time, when you run this, it doesn't get the face exactly the way the user might have believed it should be. One of the things it's supposed to do, if you're blinking, it's supposed to make space in this representation for both the open and closed eye, so they're both sort of living there. We would love to have user interaction to fix the offline computed stuff, and that's just completely inconceivable at the moment, because you would make an interaction, even researcher level interaction, you tweak it, run it for another 2 days, tweak again. It's not, so that would be something that would be great to fix. Yeah.
So
space?
We didn't use the photosynth. We actually used a different bundler for this, but oh, sorry, no, to work on the face. It can't do it at the moment. We used photosynth embeds tracks. You imagine if you follow the eye, you generate a track like the cyan curve we saw on the giraffe. Photosynth takes hundreds of thousands of those tracks and embeds them into a 3D space. We are taking 100,000 of those tracks, but we're embedding them non-linearly into 2D space, not close to linearly into 3D space. So it's quite a different problem. The mechanics of it are quite different. It's a multidimensional scaling problem, basically.
So I'm just thinking of an app, so there are avatars in these sort of online real world interact with one another. Would this be usable in there?
You mean to recover the texture map for the...
So if you wanted to make an avatar that was somehow looked like you but changed and it's running in real time because you're interacting.
Oh, yes, yeah. Except that even the tracking bit, so once you have what you would do is take the texture map, and then with every new frame you would discover the mapping between the texture map and the new frame. Our implementation of that is currently like several minutes per frame. So yeah, if you could real time that, you would have a lot of opportunities. Yeah. But that's part of the pre-process, because our output is just the motion vectors, which, yeah. Thanks.
Okay. Amazingly, it seemed to like my system instead of giving trouble connecting. My name is Jim Held. Director of Tera-scale computing research means I'm a cat herder in our central labs at Intel. We have a program of research that you might characterize as the future of multicore. It is how far can we go, how fast, what will we have to do. It's a large program, several dozen projects, a couple hundred people at the moment, and covers everything from software to hardware, usually starting from the application level and analysis of applications down, looking at usage models as well as the low-level primitives and how to best support them in hardware. So a very comprehensive program. One of the major areas of application is what we call immersive connected experiences, which I'll define in just a moment. In fact, first I'm going to introduce the concept as we describe it. It is sort of a combination of social and visual computing, so that it's a nice bridge topic between the two. What are the requirements we see in it, what our research agenda is, what the various projects are. My goal is to introduce these, not to go into depth on the actual details of the research, but vector you to the people who are doing that work. If you're interested, I'm sure they'd be delighted to correspond with you. Potentially there'll be some collaboration with the folks, both at Microsoft Research or at the universities and UPCRC. Some of the folks are here in the audience, so I'll highlight that when they come up. Others, different parts of the world, I'll mention that as well. Now, ICE comes really from a combination of trends coming together. Social networking has been growing tremendously, a very important use of computing for us to be aware of. One aspect of social networking that really uses compute on the client is the user-generated content. Now, that can be just the text that someone puts in a blog or texting in a chat room, but people are getting much more sophisticated, creating their own, sometimes rather interesting videos, and in the case of virtual worlds, much more complex 3D content. The idea is that we're moving from a world where the content displayed and used in applications doesn't just come from professionals as it does in a traditional PC game, for example. Broadband connectivity means that we can draw on a combination of the client and a rich network of servers in the so-called cloud, for example, and that the computation, one of the questions is how best to take advantage of that computation capability and to deal with the complexity that having a distributed application implies. Mobile computing is growing. It won't be too long before desktops begin to disappear or turn entirely into a local server or a specialized workstation, because so many people value the ability to take the client with them, whether in the form factor I'm using here or in a handheld device or in a combination working together, as the earlier CBIR presenter illustrated with his combination of iPhone and his Macintosh computer. Visual computing is something we're very interested in because it's becoming a major fraction of the compute use on the clients. PC clients are increasingly being called on to interact in a much more rich way. Visual computing is part of that. When I talk about visual computing, I mean much more than graphics, though. Visual computing, in our terminology, is a combination of not just photorealistic rendering of images, but also the combination with modeling and simulation that makes your interaction with that representation realistic and responsive. It requires physics, it requires recognition, as well as rendering. It requires a mix of computation, not just data flow, flop-oriented graphics processor, but the more general purpose and actually the combination of the different kinds of compute come into play with the kind of applications we think of when we talk about visual computing. So all of the different kind of very interactive application environments that, yes, include video and 3D and other visual representation, but mixed in with a representation of the world. Now, there's one other aspect that comes to what we call connected experiences. Why do we say immersive connected experiences? And that's because many of those visual computing uses draw on the fact that people want to connect to other people. That we're not just talking about the client being connected to the server to deliver computes or storage, but we're also talking about the gaming and collaboration and retailing and all the other ways in which the computer is used as a tool of communication and interaction. And so immersive as well as connected environments. In fact, we see that the direction that the web is going from what was originally very text-oriented and static stereotype interaction to add more and more graphics and video and increasingly 3D. And we see immersive connected experiences, our name for that combination and the direction that the 3D internet is going. So there are applications that draw on compute and the connection to enhance the actual world, to mix computed images and computed modeling information with video and data from the real world. I'm sure you're all aware of the applications that allow you to go to a location, see a map of it, overlay that map with a satellite picture, draw on another application to actually get a 3D representation that you can interact with, see a street level representation. So we really are taking the actual world and overlaying on it some abstractions that add information to the raw image that people are seeing. We're also creating completely artificial worlds, whether it be in a multiplayer games and massively multiplayer games like the World of Warcraft, etc., are becoming very popular. But there are also completely artificial environments that are created by the end users where they interact in unstructured ways around a structure, but not in a prefabricated, prepared game. Those so-called virtual worlds, as opposed to an environment created for a predetermined game, are becoming extremely popular. Many millions of users. Last year, 2007 actually, more than $1 billion was invested, but in 2008, in an absolutely tough economic environment, there was still almost $600 million invested, and in fact, over twice as many different virtual world investments, different companies. In 2007, Club Penguin acquisition by Disney accounts for like 400 million of that billion. So it's actually broadening and continuing. Most of the interaction is going on without really using the full potential of a computer to deliver a rich model and a rich visual environment. You see Habbo and Neopets and Poptropica, which really involve interaction through a browser and more of a 2.5D animation environment. They still have the idea of visual representation, high level of interactivity, model of the world, and in fact, commerce. Almost all of them involve the ability for, naturally, the participants to spend money to add to their environment. They involve them creating and having possessions in that environment. Some of them, like Second Life, allow that economic return to flow both ways, Linden dollars in and out of the environment. So we're getting a large number of virtual worlds, a lot of participants. It's taking hold in the youth. Most of the participants, like, well, certainly a little more than half, are preteen or younger. And so people are growing up with this as a way of interacting with each other through a virtual environment. The last bullet here on the right-hand side, I think, is particularly significant. As Second Life moved up in the Nielsen rankings of what they call PC games, these are actually 180,000 measured households. It's not survey, it's not self-report, it's actually like Nielsen rating and TV, they instrument systems and track what's used and how. And it accounted for the second largest fraction of the total minutes played, and people were spending like 680 minutes per week engaged with the virtual world in Second Life, second only to World of Warcraft. So very important, a lot of eyeball time, a lot of participants having their own economy, grabbing the consumers of tomorrow, in fact, significant consumers of a fraction of the money spent today. So, of course, interesting to Intel as a future usage model. We also have that augmented reality as opposed to the virtual world, particularly with mobile devices. The mobile devices are great to carry around sensors, cameras, acceleration devices to sense orientation and motion. All kinds of things can be packaged into that device with a wireless connection to a lot of compute resources. What do you do with it? Well, often that interaction involves augmenting what's being captured on the device with information that's centrally stored or centrally available. We've got some examples there. Being able to use the camera on the device and overlay instruction on what to do to disassemble the engine, for example, or a translation or identifying some device. Another area where we see that this combination of visual computing with connectedness and the balance of compute is going to really increasingly create new usage models that are draw on multi-core computing, not just in the servers, but on the handhelds as well. So ICE is our name for what we think is a compelling set of new usage models or uses of computers that's going to drive consumption of compute and gives us an opportunity to add value by responding to it, by giving the right kind of platforms, the right kind of processors. What does it need? Well, there are all kinds of challenges if we're going to respond to those uses. One, of course, traditionally figuring out what the demands are on the server and the client. Memory bound, compute bound, storage, what kind of compute, what kind of operations are being done, what kind of network connectivity is required. All of those are our traditional role and something we do with all of our applications that we analyze, that we get, in-house or build in order to shape what we do. There's also, though, a lot we need to do in the distributed computing realm, and I'll talk a little bit more about in the virtual world space. Well, we think one of the barriers to that really living up to its potential is really the architecture, the distributed system architecture, and we have folks working on that in our labs. We need to look at how we deal with the fact that we're going to have handheld devices as well as very powerful laptop devices and things in between. How do we deal with that diversity and the fact that there's always an installed base? You can't design for the latest. You can't design for one fixed model. How do you avoid a lowest common denominator approach to this distributed computing client model? Visual content, we talked about being something that end users were creating. As much as half or more of the cost of a title for a game is traditionally in the artwork. It's in the content, so to speak. That just isn't there in these virtual world environments. When end users are creating their own video and want to create their own 3D devices, they come up against a very difficult, clumsy environment. The ability to create a video is much advanced over the ability to create a very rich, complex environment for your virtual world, much less design an avatar that suits or represents you the way you want to. Having the ability for people to create and then move their content where they want to go, because it is their content after all, it shouldn't be just a property of each individual place they go, is another challenge for fulfilling this. And finally, how do we deal with sensors and connectivity when we're talking about the mobile devices? Now, we've done analysis on platform demands. Pradeep Dubey and the Application Research Lab has done analysis of Second Life, the client, and then indirectly from the binary operation of the server and the network connections. And we find certainly virtual worlds like Second Life have tremendous demands on the servers. Very compute-intensive work, 10 times as much demand on the servers as something like the World of Warcraft games, because of the way you interact with a much richer ad hoc environment. Clients as well really draw on the CPU and the GPU. That visual computing is a key part of what the job of the client is in the virtual world space, at least. Again, very compute intensive, very high utilization, very important to the experience. And finally, the network connectivity, it highlights another challenge. You'll see there are two lines there. In the virtual world space, you can't pre-distribute content on a DVD and draw on it. It's being created and shared with people as you come across them into the world. You move into a different land or world or part of the world and meet people and places and things that you've never met before. How can they be pre-distributed? That really places tremendous demands on the network. The ability to cache that effectively and compress it is important. Yes?
So for these numbers, are these for kind of like an okay experience, a mediocre experience, or this is like, we want, like for a great experience, is this how much more compute do you want?
Pradeep, was it a great experience or was it an average experience? I think it was an average experience. I don't think this is what we would want.
Second life experience is never a great experience.
Let's just say there is a lot of potential to utilize even more to improve it. A challenge with this aspect of ICE, the virtual world, is dealing with complexity of the environment. The number of users, the number of objects, the object behavior, the realism of the simulation, all drastically increase the complexity. It's far from linear in the number of objects. It's far from linear in the complexity, the realism of the modeling that you do. And that right now, because of our inability to really supply all that's desired, means that the current implementations are severely limited, simplifying, for example, the shapes of an avatar in determining collisions, in latency and delay effects. It's easy to move too fast in the wrong circumstances and fly right through a wall, to leave behind certain objects that you desire. So the challenges, because of delays in processing, introduce artifacts in display and synchronization and slow down the interaction. It would be infeasible to have a virtual concert to thousands of people in a virtual world environment today. It just could not sustain the interaction among that many people. Yes?
So some people have done work in sharing bandwidth. You have a whole bunch of people standing together with cell phones. They could take the union of their bandwidth by communicating with one another through Bluetooth or something like that. And they've done some demos where they can actually multiply the bandwidth. Would that be a useful feature here? Yeah.
The ability to create a richer connectivity, yes. And the architecture of the distributed system, making it more scalable, and techniques like that is part of the research that is going on in the labs. This is part of what we have to figure out how to deliver. The distributed system involves not just a given virtual world or environment like the Second Life world, but interaction with others, the ability to share content back and forth. It has both global resources to manage as well as regional things to take care of, assets, simulations in local islands, for example. And they have connections to powerful clients. Let me see if I can make this run. Compute capable, as well as limited but very sensor-rich devices. How do we design for this kind of an environment? That's what we're interested in. That's what our research is going on. Each of these pipes is a potential bottleneck. Each of these resource managers and services are a potential bottleneck unless you have the ability to replicate and scale. The ability to dynamically adjust to the client that is being used and have multiple types of clients participate is really critical. The ability to share dynamically the workload between the server resources and the client. Those are the requirements that we want to meet. Okay, so what we see happening in order to really scale is that we need to move from monolithic creations to the much more modular, horizontal building block approach to designing these environments. Essentially, same kind of thing that the internet went through. I don't know how many of you used Prodigy or CompuServe. One of the first beta programs I was on with Microsoft, I reported everything in CompuServe. Those evolved to today's web and the open platform that allows a much richer set of things to grow and anticipated things to grow and share. That's what we think needs to happen in order to fully realize the capabilities in the environment. In the visual content space, we have to move from professionally created content to the end user being able to create their own content easily and satisfy their own creativity and own what they create and move it around because it becomes an important resource for them that they value. It's their identity in many cases. And then we have to deal with the problem of delivery of content. We can't pre-distribute. We have to have ability to deliver just in time and cache effectively. So we really think that there's plenty of research necessary in order to make this kind of experience really high quality and scalable to rich environments, lots of objects, lots of people, very faithful modeling of the environment. And the challenges in each area have generated research going on. You've seen some of the initial results and glad to share papers on workload characterization. We're doing work to understand the platform demands in detail, and we'll carry those forward as we do with all of our workload analysis to optimizing our server and client platforms to support them. In the distributed computation space, we're really working with the industry on proposing modifications to the application architectures. I'll talk a little bit more about later. And research on dynamic repartitioning of the workload between the client and the different kinds of client and the central compute capabilities. A big effort. I'm going to highlight in the slides today because the research is actually in our Beijing lab, and Yimin Zhang wasn't able to be here today, so I wanted to show some of that because he couldn't speak for it. And then I'll also point out some of the stuff going on with the distributed computing that Mick Bowman is leading. So let's start with that content creation. One of the ways in which we can deal with both the distribution and the creation of content is to parameterize it. You don't want people sculpting or drawing these 3D models. You don't want them to assembling crude components. You want them to be able to customize the appearance, for example, of their avatar very easily just by moving sliders to match what they want. You want scripting to be able to interact with a parameterized expression modeler. So you don't send images, as this video is creating, to describe someone who's changing moving their features as well as changing their expression. You want to send parameters to a model that is pre-distributed. It gives you much more flexibility in design. It gives you the ability to send much higher semantic information and therefore much more compressed information over your network. And they're drawing on databases for their research, one from the Beijing University of Technology, another from the University of Binghamton on facial expressions. And I'll show you a little bit more about how in a minute. One thing we'd like to do is be able to create an avatar that represents us better, to take a picture, for example, identify the features within it that correspond to an abstract model, map that model back to the features on that picture, and take the result and map that to our model and therefore be able to manipulate the model. So what we've done is we've taken a flat 2D picture of someone, identified the features, mapped those features to a model from our database of models, and then we can apply the 2D as a texture to that model and manipulate it in 3 dimensions. 2 dimensions, 3 dimensions, but moreover, it's the person, it's me. Also, I would want to be able to parameterize a variety of things. The expression on the lower left, for example, going from neutral to happy, configure the gender characteristics of my avatar or my characters. I'd want to be able to parameterize the dynamic interaction and map it to a particular instance of a person. So capture this kind of change of expression, apply it to an image, any kind of image where I can identify the features, and then have the resulting expression shown in that face. Facial features, even ethnicity, all can be done by use of that 3D database, treating it as a model, allowing what we used to call morphing techniques to make it a continuously variable transition. This to me was science fiction when I was growing up, right? You answered the phone with an avatar that looked perfect even though you had just gotten up. Or maybe you represent yourself as an avatar of Brad Pitt or Arnold Schwarzenegger or whoever. You can do that with the technology that's being developed on the research in content tools in our Beijing lab. You do want to be creating 3D models, not just mapping textures, manipulating, doing the expressions of an avatar. And that's a tedious process that, again, is very expensive to do. And so what they've developed is a tool to take pictures around an object. It provides view planning to suggest what would be the best camera positions to capture an object, and do the image-based modeling. In other words, tracking and doing correspondence analysis against the images and turn that into a 3D representation and extract the texture, creating therefore a 3D model that you can then use and animate in your virtual world. So going from something that is done by experts and expensive and tedious, might be improved with a 3D scanner, to something the ordinary person can do by the appropriate use of their digital camera. We have work at the Intel Research Seattle lab on what we call everyday sensing and perception, and our goal is to be able to infer context from sensors in your handheld device that are accurate 90% of the time for 90% of your day. 90% is actually very hard to do, and something you're not going to be able to do without visual information, without video capture and vision and recognition. Moreover, if you're talking about doing it with sensors that are in a handheld, one of their fundamental problems is the ability to do pre-processing on this device to reduce the bandwidth required and the latency, and pass it to the server where the heavy-duty compute goes on, and then the result comes back. And so they're very much dealing with the ability to create a synopsis in order to reason on it with much more compute power in a central compute resource. We're engaging the virtual world community through OpenSim. Allows us to work with a wide range of industry partners in a diverse community, Microsoft, IBM, Intel, a wide variety of participants on this simulation environment for a virtual world. We have been working with partners to try to put together a roadmap for virtual worlds in order to try to improve the success rate or the likelihood of success of all these virtual worlds that are springing up, to understand what would make them more viable, how that people could be more productive with their investments by taking all of our state-of-the-art industry-wide thinking and making it available. We are creating, I moved too quickly. There we go. How am I doing for time, Jim? Great, thank you. We wanted a test bed that was computationally interesting and challenging, that would give us content and experience with real-world customers. So we partner with the SIGARC and IEEE in order to create a science sim, a simulation environment for representing the results and the interactive environment for Supercomputing 2009. And so the idea is to have the opportunity for interactive presentation of results in a simulated environment be part of something this high-performance computing community would really be able to take advantage of. Both a chance to show off as well as a future education tool. And actually the result of our interaction has been concrete. I think it's been like a 10x improvement in scaling so far from architectural changes and suggestions that we've proposed to the OpenSim community. We've got an IATF MMOX OGP proposal in to create the interface, or actually use industry standard interfaces to make the virtual world simulation environment more scalable. And I'm sure Mick would be glad to fill you on exactly what that entails. So we're very actively engaged in this open environment to facilitate what we think is something people are interested in, could be able to use, would exploit the value of the computes we can deliver, but needs some architectural leadership from industry players like Intel and Microsoft. This ICE research actually ties together with our other main initiatives. I mentioned how we have a Tera-scale computing initiative, and the performance to support that and the platform characteristics that will allow the kind of computes to be delivered, and the balanced platform with the right acceleration, memory, bandwidth, compute capabilities, all of those are part of the Tera-scale computing initiative. We have another large effort we call Carry Small, Live Large, which is the idea of getting tremendous benefit from our handheld computers, working in concert with clients, peers, and the server world that involves the use of sensors and wireless connectivity features that the augmented reality research is part of. Visual computing is really a big thrust for us. We've been talking about work underway to develop the Larrabee architecture, and I've talked at SIGART and elsewhere about the characteristics of Larrabee. We're making a big investment in that space for future product. That needs to be fed by research. We've had long-standing relationship with Saarland, so we put a large amount of money into what it will be our largest lab research effort in Europe. It'll be part of our Intel lab environment or collection. I'm missing the word, in Europe. Jim Hurley is part of our CTG visual architecture research lab in our microprocessor group in CTG, and colleagues at Saarland, we've actually again been working with for some time, and others in Germany that are going to be participating on a really rich research agenda that again is much more than just raw graphics or 3D. The concept of visual information recognition, capture, and the simulation and output, what it makes possible in terms of interactions, the human-computer interaction that's possible given these modalities. So again, another big investment in what is very much the underlying technologies for the immersive computing environments. So we think this is an exciting area of applications. We sort of come way up from our previous talks about the enabling algorithms technologies to a much broader view of the ecosystem trends, what it's giving rise to in usage models and applications. We think it's one that's going to draw on all of the research we've described so far to deliver something that end users are already interested in, already beginning to pay for, and will make use of our processor and platform technology. Any questions?
Thank you.
Okay.
Hey, good afternoon. My name is Phil Chou. I manage the Communication and Collaboration Systems group here at MSR, and we do a bunch of work in telepresence, and I'm also involved in a cross-group initiative in telepresence here. Telepresence is a word that was coined by Bill Buxton in the early 90s as part of the Ontario Telepresence Project. He meant it to be rather broad in interpretation. Technology to support a sense of social proximity despite geographic and or temporal difference. Today, telepresence in the industry takes a narrower view, that of a video conferencing experience that creates illusion that remote participants are in the same room with you. It's more of a teleimmersion definition, I think. But the best way to understand what that means in the industry today is to take a look at this 30-second Cisco commercial.
So,
welcome to a network where body language is business language. Welcome to the human network.
So you've just seen a high-definition, full-sized, life-sized video conferencing experience that's so compelling that one participant forgot that his counterpart was actually remote. This Cisco telepresence system along with others like it, costs several hundreds of thousands of dollars per room. And of course, you need at least 2 rooms to make it useful. And that doesn't mention the additional tens of thousands per month of operating cost. So it finds a rather narrow market, but there is a market, popular among executives in particular. Microsoft itself is purchasing a bunch of these things. But the general feeling we have at Microsoft is these are somewhat akin to the mainframes of the 70s. And so there's a lot of opportunity sort of downstream from that. So one of the takes we have on telepresence in research is that it could be closer to ubiquitous computing, which is a notion that Mark Weiser in the Computer Systems Lab at Xerox PARC had promulgated in the early, 88 through 95. And the idea is that instead of computation being delivered through boxes on your desk or from the back room, it actually computation would be woven into the fabric of the environment. And so they built a bunch of devices, PARC tabs, pads, and live boards, which are today's PDAs and tablets and interactive whiteboards. An example today might be Craig Mundy's, our CTO's, conference room over here, in which the room, every surface of the room is some interactive display and interactive surface. All the walls, the table, and everything. So there, the room is the computer, and that might be what ubiquitous computing might be today. We're interested more in the communication aspects of ubiquitous computing. So this was called Ubiquitous Media by Buxton in the early 90s. And it really is driven by sensing and rendering devices, input and output devices, both for audio and video, meaning microphones, cameras, speakers, displays, sort of the ubiquity of those things, particularly in cell phones. So all of us have all 4 of these modalities sitting in our pockets. And there's also more infrastructure-like things, laptops, desktop monitors, conference room devices, IP cameras. We have these things here, we have I can see 6 different cameras in this room, so lecture rooms are highly equipped. Our highways, we have hundreds of cameras publicly accessible just looking at our highways. Cities like New York and London have thousands of cameras just connected to the police network. So these devices are really totally ubiquitous. Even if you look at a regular office, here's a picture of my office. There are many devices connected to the internet, my laptop, my phone, my desktop, and my camera phone, which is taking this picture. And each of those devices has 4 or 5 or more high bandwidth sensors or rendering devices. So there are 25 broadband sensing and rendering devices in this picture. Over here, everybody's bringing laptops and so forth. I'm estimating that there are 55 to 70 microphones, loudspeakers, cameras, or displays in that conference room. So they're really ubiquitous. And the question we ask is, how can we use these devices to assist with better communication between people? So there are several opportunities. One could be, for example, better audio capture. You get microphones that are closer to the people who are actually speaking. Similarly, close-up views of participants. The laptops may have cameras that are actually looking at your face. You can use this ad hoc array of sensing devices to locate people in space in the room and help people remotely understand what is going on in the room. For the people in this room or for people in the remote rooms who are listening in on this conversation, there's spatialized audio to get a better sense for these guys over here to get a better sense of what's happening spatially in this room. Over here, there's flexible use of display real estate because there are lots of displays all over. So there are a lot of opportunities. I'll go through some of these. This is just showing where all the 25 devices are. So here's an example of using an ad hoc array of microphones, in this case distributed on the laptops that are of people in the meeting rooms, to do sound source separation. So putting 4 people on their 4 laptops into separate sound channels. If they're not separated, one of the, let's say laptop number 2, its microphone sounds kind of a mixture.
The lawsuits claim the company distributed illegally copied software through the internet.
Most of the pirated software probably comes from overseas and is
They're talking over each other and
at a deep discount and sold to consumers.
We want to put them into a single channel. So let's say channel 2 basically cuts out the first guy.
Most of the pirated software probably comes from
guy.
overseas and is purchased by distributor.
And we can build in to the source separation location information. So we either using time of flight based techniques or energy based techniques. So here's a picture, an overview picture of people in a room gathered around microphones glued to the desk. And this shows that we can locate through sound that's uttered by only the people who are talking, so no pinging sounds or anything in the room, that we can jointly locate the active speaker here in this red dot and all of the microphone locations, which are accurate to the ground truth down to a few centimeters. And if we use energy based, it's maybe a little less accurate, but we don't need the tight synchronization between devices. So what you can do, you get the source separated and you get the sources located in space, then you can help the other people in the other remote rooms understand what's happening spatially. So instead of the traditional mono signal in a room, which maybe sounding like this.
Oh, then you have to pick 3 places?
Yeah. So
What
but
if
we've
we
got
all
one.
agreed on the first one?
Hey, Greg, we got one done.
I'm putting a square around Hawaii.
Yeah.
So let's move on.
Okay.
So that's a traditional mono thing, and only the people in the middle can probably hear the stereo. But if they are spatialized, it's easier to tell what's happening in the room, how many people there are.
Yeah. So but
What
we've
if we
got
all
one.
agreed on the first one?
Hey, Greg, we got one done.
I'm putting a square around Hawaii.
Yeah.
So let's move on.
Okay.
So it's taking advantage of cocktail party effects that people have. Of course, if you do these spatialization tricks, then you have to deal with the acoustic echo cancellation problems that happen in the room. So if I'm in my office listening to spatialized audio and I'm talking into my microphone, that's being interfered with by stuff coming from now 2 loudspeakers instead of just 1, and there are some inherent ambiguities that go on with 2 loudspeakers. We need to cancel out what's coming out of these loudspeakers so the guys back in the conference room don't hear what they've just said. But fortunately, because we're able to control the spatialization, we're able to disambiguate anything here and cancel out what comes in through the microphone. So here's a concocted example of what the microphone may hear. You're hearing now stuff coming, spatialized audio playing out here, and you're hearing a mono signal.
A speedy man can beat this track mark.
That's actually a mixture of spatialized stuff.
Here's your chance to learn about how Outlook gets you.
This is a double talk test.
And that was just the near-end talker talking. And now you can hear that most of that stuff goes away except when she talks.
This is a double talk test.
So that's all for ad hoc microphone arrays, and the same sorts of things can be done with camera arrays. So we have cameras on all the laptops that sitting in front of you. And one possible thing to do is for the remote person is to look at the screen, and every moment there's selected the best, the speaker who's talking, the active speaker. So it's select the best camera at any possible moment, and that's sort of a traditional way of doing conferencing. You could also show all the cameras at once in maybe a Hollywood Squares type of thing, so you can actually see all the faces, how are people reacting to what other people are saying. But we were inspired by some of the photosynth work to try to get a better spatial sense of what's going on in the room. So when people are looking in one direction, the remote person can understand that they're looking, the person is looking at, who's talking or whatever. So we have this meeting viewer, which essentially has this 3D context view and then an active speaker view over here. And I wish I could demo it on this laptop, but I'm just going to have to show you an old version by video. And over here, the user is trying to manipulate the three-dimensional scene to try to figure out, well, to get the best view on who's talking. And so these people are kind of arranged into the three-dimensional space. We're also looking at mobile things, trying to augment phones with something as simple as stereo earbuds or goggles. I won't be talking about these today, though. We're also looking at what we call embodied social proxies, which are essentially, George in a box. You carry him into a conference room and set him up, and you can talk to him. And things that are related, other kinds of stand-in devices, some robotic type things, some that just sit on your desk. What I want to go into a little bit more detail, though, about is not those things, but more what we're doing along the lines of immersion. So how we're evolving immersion from things that are just sitting around, you're sitting at your desk, to things that are basically taking wider and wider fields of view and involving you in an immersive experience. We have the idea that you might, as an individual, just sit down at a desk somewhere, have a very wide field of view, and then you're talking with your remote counterparts who are all distributed in different continents or whatever. But you're sitting around a common virtual table, and as more people are added to this table, as more people join the meeting, the table may grow a little bit bigger. People slide to the side and make room for the new person. The audio, is coming from the person that is talking. You see the people from different angles depending on where they are sitting around the table. We're in a common environment. The environment may have tools that support the meeting that's going on and so forth. So there are a number of immersive cues that we're taking a look at, both in audio and video. Peripheral awareness is an important thing, we believe, so that's why we're looking at large fields of view and surround sound. Visual consistency is important, the consistency between my environment and the remote environment. And if you have multiple people, the consistency between their environments. And of course, sort of spatial cues. Andrew showed a nice video where the occlusion cue was all kind of messed up. Let me just talk about the last two on this list, what we're doing for motion and stereo. So motion parallax, we sometimes call monocular 3D, because even if you have only one eye, you can get a sense of depth through your motion. So what you see on the left is a video of how we can change what's displayed on the screen as a function of the position of the viewer in order to get a sense of 3 dimensions.
Can't help but notice that the viewer is moving a little slowly. Is that because there's some frame rate issues there?
Not so much from the generation, but the tracking in this case is done by a magnetometer, and there are some issues with that. After this was made, we started tracking using face detection and head pose estimation, and that's actually what you see on the right side. So here, Chou is looking at this screen, and this red rectangle is what's detecting his face and size right now and driving his screen. And we're also now doing a little more sophisticated stuff with head pose estimation. We're also looking at stereo 3D, typically using for display systems existing technologies such as autostereoscopic displays or displays where you need some kind of goggles. These require, even just putting images on these things actually requires a fair amount of, there's a lot of data. So for each pixel that you're trying to, you scan through this thing, putting pixels down on the display, and each one comes from, say, a different camera. So if we have a upstairs we have a 5-view autostereoscopic display. We have 5 cameras feeding this display. For each pixel that we output to the display, we have to pick it from one of the cameras and at a particular position on the camera depending on how the cameras are calibrated. And so we have to do some bilinear interpolation, for example, on each of those cameras. And we just couldn't fit it into our 4-core machine, but we squeezed it into the graphics processor. But there are some issues even doing elementary things here. That's on the display side. Of course, you need to capture multi-view imagery. So image-based rendering is an important element of that. And so we do spend some time trying to do camera array stuff and view interpolation. I don't want to go all the way to the end. In order to put people into a common background, you have to actually remove their existing background. So foreground, background segmentation and replacement is important. So, with enough computational power, you can do a pretty good job at it. This runs many times real time, so we've been looking at things that are much faster, such as using infrared depth cams to help speed that up. And they do a remarkably good job in terms of real-time performance. So easily getting 30 frames a second here, but they're not so good at hair. So we have to kind of find the right balance between some of these technologies. Another alternative to the image-based rendering things would be to go more on the graphics route. And of course, we've been looking at using avatars, and they're necessary for representing remote people who don't have audio and visual, don't have video cameras trained on them, like if you're on a mobile phone. And then, so finally, we're trying to put all this together into an experience, building these things, and it just the list of just for video processing. There's no audio processing listed here, but just for video processing, there's a lot of different steps that we have to go through. On the sending side, there's after the camera calibration, camera capture, distortion correction, viewpoint interpolation, foreground background separation, the encoding, networking stuff, and then on the receiving side, do some face tracking to figure out where is the person looking, trying to determine where his viewpoint is, and then after receiving stuff from the network, decoding it, doing some final viewpoint interpolation stuff, and then the scene synthesis. And this is pretty close to linear with the number of other participants in the meeting, because for each other participant, each one of them has a unique view that you're trying to send to or receive from. So I wanted to mention that besides getting an immersive experience, part of what's important in communication is actually various kinds of scene analysis, some of which we've seen already with like where are people spatially. But there are others. So for example, Chou here is say using this fisheye camera shown here to direct where the pan-tilt zoom camera should be pointing at. So we have to figure out, well, what are the salient features, what are the gestures that are important to capture. So one reason scene analysis is important, and this is a bridge to the next, to Lili's talk, is social interaction analysis. So you want to know where people are looking. Are they to whom are they looking? So that maybe the avatar that you're looking at could be looking back. So that you can measure things like who is influencing whom, who's consistent in their views, who is agreeing with whom and disagreeing with whom. And you could use these within the context of a single meeting to give feedback on, you're talking too much. This guy isn't saying enough. Is the meeting really constructive? Let's say it's a brainstorming meeting, or is somebody dominating, or maybe that's the way it's supposed to be because it's a presentation. And then over time, you can infer from many meetings, social interactions that are being analyzed, what are the groups, what is the social interaction network? What does it look like from real meetings conducted through these telepresence systems? So I will just end by going back to the ubiquitous communication idea. This is just a shot of the heterogeneity that we live in and will continue to live in. Just a statement there is no single telepresence or communication device. There will be plenty of things, ranging from just mobile phones all the way up to the most sophisticated conference rooms. And the implications for this on architecture, I guess, is communication between. There's a lot of data flowing between the endpoints, so data is a huge thing, and also the heterogeneity means that it's not really clear where the computation is going to go. I mean, the mobile phones won't have the same capabilities as these high-end rooms. The cloud isn't even pictured here, so you can imagine services in the cloud. Some of the computation could be used to save on the communication bandwidth. So there are all these kind of interrelated issues. And I'll just use that to close. Thanks.
Any questions? So when are we going to get this film? I'm tired of getting on airplanes.
We're actually, one of the next things we're trying to look at, we're talking with Dennis actually, is how to deal with large-scale meetings such as this one, or conferences that we go to, and are there any ways to help do a poster remotely, for example? Yes.
Does speech recognition technology fit in this anyway?
Yes, and machine translation technology. You would certainly want to be able to, bridge cultural and language barriers like that.
But also like making minutes automatically.
Oh yes, so for summarization of meetings, yeah, absolutely. Yes.
What is the most sophisticated of the things you showed us today that you've actually used to hold a meeting?
Well, actual use, we don't have a picture here. But we did here's one. This group, our group, did this roundtable device, they call it. So it's like a Polycom speakerphone, but it has a stalk on the top with a 5-camera thing on the top, and you do image stitching. And so it's 10-year-old research technology, but it came out just a few years ago in product, so we actually use it pretty consistently, and it's in most of the rooms in this building.
Is there more sophisticated or not? I don't know.
Is it sophisticated? 10 years ago, maybe, yes. All right, thanks.
Thanks, Bill.